if you just do it, it'll turn out okay. Hey, everybody, we're back for more Talking Time with Caffeine, the only podcast where we talk, do some caffeine stuff maybe, and we talk about whatever the subject of the day is. But first, I got to introduce my two new guests, right? Or they were introduce themselves, actually.
You want to go first, Leo?
Yeah, just give me a second. I got to take a drink here.
I don't have any caffeine. I apologize.
Gotta wet my whistle. Yeah, I'm Leophilius, otherwise known as Leophilius, but most people can't pronounce that, so they just call me Leo. I do have a YouTube channel. Whether that's fortunate or unfortunate depends on who's hearing it. I do a lot of science education and science communication. My focus is primarily on astrophysics, cosmology, and quantum mechanics, but I do touch in some other subjects here and there, a little bit of philosophy and a little bit of politics as well.
All right. Your turn.
Sweet. All right. Hello, y'all. I don't know how to pronounce my name because I misspelled it when I made it. So I've heard Ogre, Orge, or Orje, or Gay, whatever you want to call me is good with me. I too have a YouTube channel. Mine is not as good as Leophilius is, but I like to try. I mostly focus on crappy YouTube videos, making fun of flat earthers and mud fossil people and stuff like that. On a personal side, I have a background in geophysics, and I think that stuff's cool, so I like to talk.
Awesome. Well, the reason you're here is partly flat Earth, but a little bit beyond that. You see, I've been, for the last 2 years, I've been hitting my head over the people still think the Earth is flat, but I've been also thinking, if they think the Earth is flat, does that also mean that they also believe that they're also geocentrists? So I don't think you can be a flat earther and at least a heliocentric. I don't think it works that way. That would be a weird orbit of the Earth if it's flat and geos and
yeah, usually those two don't work. I agree.
Yeah, but anyways, I was watching the after show with my friend Dapper Dino, and I actually asked them, and they explained how they know that the sun and everything goes around the Earth. So people actually used to think that a long time ago, didn't they?
Oh, yeah.
I'd say that was prevailing knowledge for quite a while, yes.
Even after they knew the Earth was round, they still thought we were the center of the universe.
Mm-hmm.
Mm-hmm.
So about when did they start realizing that was the wrong way of thinking?
I actually don't know the date. All I know is it started, I believe, with Copernicus.
Yeah,
he developed the Copernican model, but I don't actually know what. If I had to guess, I would say probably somewhere in maybe the 14 or 1500s.
Yep. I think late 1400s, early 1500s.
Okay.
Looks like, yeah.
And he made the first discoveries, then Galileo later made more discoveries about it.
There's a whole long list of astronomers on the Copernicus heliocentric model. Galileo's one of them, of course, but big long list of old dead white guys.
Yep.
Yeah. I heard one of the things they thought of, at least if I remember history, that some of the stars they saw turned out to be planets. Did some kind of weird movement in the sky, and instead of circling, they went some weird.
Isn't it? Correct me if I'm wrong here, Leo. Isn't the term for planet was comes from the word wandering star or something like that?
I believe so. I think it had something to do with that.
Yeah, they noticed for a while that some stars would move, and why is that? They didn't really have a good explanation until we later discovered the planets and the rotation stuff like that cemented into the model. So Mars, of course, being a key example, Mars very obviously moves around, as does Venus.
Yeah.
Yep.
So why do they still think that everything goes around the Earth?
Arrogance would be my assumption. They think that the whole universe is centered around humans, despite the fact that it's not. And so to retain that feeling of grand importance, they put humans and the planet they live on literally at the center of the universe.
Yeah, that and the general want of conspiracy theorists to have everyone against them be I can't remember the word off the top of my head, but like you have to disagree with everything else just because you can't really be a good conspiracy theorist if you believe other people. That kind of goes against the definition.
Mm-hmm.
Well, they do believe other people. They believe the wrong people.
Contrarian.
Yeah, exactly. Yeah.
But,
yeah, they like being contrarians.
Oh, and there's also a heliocentric model. It's not this. It's still not right, but it's better than the geocentrist.
One where the sun's the center of the universe. Is that what you're talking about?
I think it might be the Tychonic model, where all the other planets go around the sun, but then the sun still goes around the Earth, and the Earth is still at the center of the solar system.
Oh, okay, that's
often referred to as the Tychonic model.
That's a real cluster, I imagine.
Yeah, most people that I've met or had discussions with that are geocentrists tend to hold to that model, but it's still wrong.
Do they hold to that because it makes the epicycles less dumb, or like what's the benefit of that?
Yeah, I think it has something to do with that. That it's a slightly, marginally more defensible model, but it's still wrong.
And the stars go, and all the stars go around the Earth too.
I believe so. Yes. That some. I can't say that this would be true for all, but I know in the case of, like, say, Robert Sungenis, Rick Delano, and their ilk, and they're two pretty prominent geocentrists, they believe that the entire universe literally rotates around the Earth. That the Earth remains fixed. The Earth doesn't rotate. It doesn't orbit. Everything orbits around the Earth.
I didn't know we were that important.
Neither did I.
That's exactly the reason, right?
I don't feel that important. Shame.
But so how do we know for definite that the Earth is the one moving around the sun and not vice versa?
I would say that the primary evidence that the Earth and that all planets are going to orbit stars, assuming that we're not talking about rogue planets here, obviously, is going to be just the consistency and the applicability of things like the why am I drawing a blank? Not Newton. Kepler's laws of planetary motion.
Yep.
That they made predictions we were later capable of confirming. When we've observed solar systems other than our own, we've noticed that the planets orbit around the stars. So I would argue that the primary reason that doesn't require more complicated physics would be Kepler's laws of planetary motion. But then Newton's laws also help, because one of the things that Newton tried to do was derive Kepler's laws of planetary motion from his laws of motion, which he was capable of successfully doing, which demonstrates that both Newton's laws and Kepler's laws are consistent with reality. They comport with what we observe, and they corroborate each other, which strengthens, in my opinion, strengthens greatly the utility of both of those physical models.
Yeah, I would agree with all that. I would add, of course, we do have satellites. We do have, images. We can, things like seasons and eclipses work this way. You can see eclipses on other planets. The moon's casting a shadow on Jupiter, stuff like that.
Mm-hmm.
All these things work best in the heliocentric model. And to backtrack a bit from Leo, even the basic idea of gravity and how that works only works with a heliocentric model. You need the biggest thing in the center, right?
Yep. And that was what Newton, that was part of when he developed his law of gravity.
Yeah, the way you teach this to like high schoolers is, the bed sheet example. You take a bed sheet, make a taunt, put like a bowling ball in the center, and flick a golf ball around it. The golf ball is going to go in circles as it heads in. You switch those two, put a golf ball in the center, try to roll a bowling ball around the outside. It simply doesn't work.
Exactly.
So, I mean, you have to throw out literally the entire book of physics if you want anything else to rotate.
Yep.
I think you mentioned that. That sounds familiar. I think we did something like similar to that in elementary school with a parachute, like a
exactly.
parachute thing. I think we did that back in the 80s.
Yeah, but basically every public school child has done that or seen a video of it because it just works so well, as an example.
Another big reason that we know that the Earth orbits around the sun and that the sun is at the center of our solar system is when we launched both the Voyager 1 and the Voyager 2 probes, and when we've launched other probes that go to the sun, or like I believe it was the Juno probe that was sent to Jupiter, we model their paths, their trajectories, when we need to launch them, when they're going to be returning, all based on the model that the Earth is orbiting the sun. And it works beautifully. So there's something else that we actually do in the real world that thoroughly comports with how physics tells us the solar system is structured. I've never met anybody that's been able to show viable launch. I don't really want to use the word trajectories, but all of the mapping that they do for launches and things like that. I have never seen anybody develop one of those that would work definitively with a model where the Earth is at the center of the solar system.
Well, probably I don't know the true or not, but probably most of them would. Everyone, all of them, but they might say, "Oh, this doesn't matter. All that stuff was faked anyways."
That would probably be a response.
Yeah, and then
we never actually launched anything.
Yeah, once you start throwing that stuff in the trash, I mean, what do you have to deal with? I think throw everything in the trash that unless it agrees with them in their mind.
I think some people were even, I would say, worse than geocentric. They don't think anything else is out there anyways. It's just all lights, pretty lights in the sky.
Oh, yeah, the dome, what's that, firmament around the Earth and all that crap, yeah.
Yeah, I think it's around the Earth because there's nothing there. It's all pretty lights.
Exactly.
But anyways, so have you ever had to on your channels ever had to argue against? A lot of people argue about flat Earthers a lot of time. You ever had to argue against geocentrism on your channels at all?
Yes, but not on my channel. Like I said, I did have a debate with Robert Sungenis, who is, despite what you may hear, is not a doctor in anything, on modern day debate on whether or not the Earth is at the center of the solar system and the universe. And in that debate, he, at least to me, demonstrated a very, very lax understanding, not just of the basic classical physics, because that's really all you need to understand to know that our physical models are correct, but that he had an even more lax understanding of special and general relativity.
Yeah, I remember watching that debate, and it was he quickly degenerated into attacks and no, you're wrong because I said so, and yeah, it was, he didn't bring anything to the table. Yeah,
exactly. A tactic that he used that I've noticed from a lot of geocentrists is they don't bring any data, they don't bring any observations, they don't bring any experiments or any evidence or anything that would corroborate their model. What they do is they pull a bunch of cherry-picked quotes or outright quote mines from a bunch of famous scientists that are completely out of context, scientists who don't even agree with their conclusions, and then argue, see, Albert Einstein made this statement that I pulled completely out of context, where he said we can't actually experimentally confirm that the Earth is at the center, or that the sun rather is at the center of the solar system, so therefore Albert Einstein said it, so it must be correct, which is in and of itself an argument from authority. Even if it's a relevant authority, it becomes an argument from authority when the only argument you're giving is their authority. So they've got 3 or 4 fallacies wrapped up into one argument here.
It's like when they say, probably like when people ask a geologist about evolution or biology. I mean, they're good on that, but they have nothing to do with the subject we're talking about.
Yeah, exactly. You ever been asked anything about evolutionary biology, Orge?
Oh, randomly all the time. Yeah, and I always preface with not my field. I'll say something, but don't take my word for it.
Exactly.
I don't like things that are alive and move and gooey. That's not good.
Off topic, but it's like they think once you're smart, you know everything about every scientific topic in the whole world.
Because that's how creationists and flat Earth and stuff have to be, right?
Yep.
I mean, you go to any creationist live stream, you can bring up literally any topic from the field of science. They're going to tell you why they're going to be able to talk about it. That's not how it works.
You've got their astrophysicists talking about evolutionary biology. You've got their geologists talking about astrophysics. You've got their evolutionary biologists talking about advanced areas of chemistry, but all while at the same time they're rejecting information from the actual relevant experts in those fields.
Yep.
It's like back to astrophysics, like they talked about evolution. They're talking about well, then where'd the Big Bang come from? Like, well, that's a different subject entirely. I mean, it might be connected some part down the line, but where the Big Bang came from didn't have nothing to do but how cells divide or why people give birth to people give birth. Nothing to do with each other. But anyways, you mentioned Kepler. What did he do?
So I believe I don't know if it's Johannes Kepler or Johannes Kepler. That one I actually don't know. I'm sure it could probably be.
You're not an expert in languages too?
No, I'm not. But he developed his 3 laws of planetary motion. I don't know all of them off the top of my head. I do know that one of them was that the orbits of planets are always elliptical, but the other 2 I can never remember right off the top of my head.
That was before Newton, you said?
Yes, just before Newton.
Okay.
I don't know if they were ever alive at the same time, but Kepler, his 3 laws were developed, I think, less than 100 years than before Newton developed his laws of motion.
They used to think it was more circular than.
Yep.
Mm-hmm. Yeah, they used to think they made perfect circles,
mostly for simplicity's sake. Because why would God use a different shape? Circles are perfect, sort of thing. Yeah, but then science showed up and math showed up, and
it's another thing I learned back in elementary school too. That some people are thinking about the elliptical orbits, but how we're actually closer to, at least how we're closer to the Earth, closer to the sun in the winter time, but the tilting thing affects, and we're further away in the summertime, but again, the tilt.
Yep.
So, does that mean when we're I can't talk. When we're in winter and they're in the south in the summer, are they actually hot? Is their summer hotter than our summer since they're closer and tilted?
I believe, I think so, but I'm not sure.
I think you're right there, but there's other factors to that. The amount of water in the southern hemisphere, water is a good heat sink, stuff like that, and the distance really isn't that stupid.
I was curious about that. Even though it's like a few extra million miles, I guess, doesn't make that much of a difference. I was just curious about that.
Yeah.
So really quickly, I did want to give what the Kepler's 3 laws are. Okay. The first one is the orbit of a planet is an ellipse with the sun at one of the 2 foci. 2, a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. And 3, the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit. And the second one is very interesting because it starts to imply what we've learned through general relativity, that the closer a planet is to the sun, the faster it will move, which is general relativity will tell us because it's deeper within the sun's gravitational field, and thus there's a greater amount of gravitational potential energy, and so it will accelerate.
And that's why Mercury and Venus are faster than we are.
Their years are a lot shorter, exactly.
Mm-hmm. Yeah, I don't know if it's true or not. Maybe outdated news. I heard the closer, or maybe I just heard it wrong as a kid, but that the planets closer to the sun rotate slower, even though they revolve faster.
Rotate about their axes slower?
Yeah.
I actually don't know if your distance from the sun would have effect. I would assume it might have some effects on rotation just because of a change in gravitational field naturally.
Okay.
But I don't know because I know Venus rotates very slowly. I know that Mercury rotates very slowly. I can't say that that's a result of their distance from the sun, or
Okay.
more just a result of how those planets formed.
Okay, and you don't know it.
It
If-
seems
if-
to be related. Uranus Neptune. No, wait. No, never mind. Jupiter has the shortest day. Jupiter's day is shorter than Neptune or Uranus's, and Venus and Mercury have super long days.
Mm-hmm.
Okay.
So it doesn't work 1-to-1 because otherwise you
Okay.
expect like Uranus to have the longest or Neptune. So
Okay. Well, that's something I remember off the top of my brain from a long time ago.
yeah, it's relative, but it's not an exact measurement because the longest day is actually Venus, not Mercury. I had to look it up, by the way. I don't have that memorized.
What the thing? I guess the good thing and bad thing about now than back then is we have more we have more availability at our fingertips than we did like 100, 200, 500 years ago. But we also have bad stuff at our fingertips too. Information and misinformation can spread a lot faster than it could back then.
And why Leo has to argue with geocentrists.
Makes for interesting discussion for the audience, though.
There you go.
Yeah. So, what did Copernicus bring to? How did he discover that we were run the sun and stuff? Or do we?
I actually don't know all that much about the specifics of how Copernicus came to develop his model. If it was just kind of if he was working on a hunch, I don't think he was. I think. And correct me if I'm wrong, Orge, because I feel like you might know a little bit more about the history than I do. But I think it had something to do with that. We knew that light hit the Earth at different angles. So we thought that if the Earth is a ball, maybe the sun is a ball. Maybe the Earth is going around the sun. I'm pretty sure there were things that he utilized to sort of intuit the conclusion that the Earth orbited the sun and that the sun must thereby be at the center of the solar system, but I don't know the specifics on that.
Yeah, I'm trying to knock back into those conversations from I want to say, well, first of all, we're talking so long ago, you can't quite know for sure.
Yeah.
They didn't write down their diaries too well and stuff like that. You only have to go off their published literature.
You mean they didn't put like a video vlog on YouTube back then?
No, they did not. No, medieval YouTube was not very popular. But yeah, to my knowledge, it was a little bit of because I want to say he was a priest, right? Was Copernicus a priest?
I don't.
Most everyone that was scientist back then was. So
I think he was. I know he was like a polymath. The dude was. I mean, he did stuff in physiology and medicine. He did obviously astronomy and physics and mathematics and a bunch of other stuff. So I mean, yeah, I wouldn't be surprised if he was a priest. But
most people back then until the printing press came out, you had to be a priest or a monk to be able to. Unless a royalty had to either be a priest or a monk to learn how to write, anyways. Most of the time,
he has a doctorate in canon law from the Catholic Church, so he was some sort of But I want to say like it was a bit more hunch based. Like he thought something was weird, and then being super genius that he was, looked into it. But I'm not super on that myself. I'm scanning Wikipedia as fast as I can. I promise.
Okay. But as we look at there, when was the
Tycho Brahe and all them too? Tycho Brahe is cool.
When was the telescope invented? Was that before him, after him?
That wasn't. Didn't Galileo invent the telescope?
Yes.
Yeah. Well, and Galileo was 1400, 1500s.
Yeah, I think Galileo was after.
I wasn't sure if he invented it or just made it useful to. He just used it for something besides looking at ships. Like, I wonder what happens if I look up the stars. Oh, wait a minute.
1609 is when he invented the telescope.
Yeah, Galileo.
Oh yes, this would have been after Copernicus.
Yeah, like you said, scientists they build up on each other. Like, not like.
Oh yes.
Like,
there's if you ever see the new Cosmos with Neil deGrasse Tyson. He has a very good episode on Tycho Brahe that goes over this, like from the other guy's conversation. Not the king, but like the Jack of this stuff, and it's real good. Every episode of that's real good. So,
Okay, so let's look at Copernicus. Do you know anything about Galileo and what his telescope helped discover about our orbits and stuff?
I know he was able to observe in quite spectacular detail the moon, Jupiter, Mars.
Yep.
What other planets did he? I think maybe some moons as well.
Well, the Galilean moons, yeah.
Yeah. So which were those were Jupiter, some moons of Jupiter, I believe. The first
Yes,
five or six or something like that.
I want to say 4, but don't quote me.
4. It might be 4. Yeah. And I think that just those really help show us that the Earth is a sphere because, well, I'm looking at all these other bodies in the solar system and they're all spherical. The Earth must be too.
Yep.
I don't know how much of a role Galileo played in particularly the heliocentric model. I'm not saying he didn't play a role at all. I just don't know what role he played in that. If he played a role in it.
I want to say it was still like, this is the time of the church dominating all of culture in Europe, right? So I don't think the heliocentric model was just like accepted after the book was published.
Yeah. I do think. No, I'm sorry. Go ahead.
Galileo was like one of the nails that finally, put in the coffin, saying, "Let's do the science of it," leading to the Renaissance and what have you. So.
Mm-hmm. I do know that he championed the Copernican model, the heliocentric model that Copernicus developed, but I don't know how much, if he added anything to it or if he was just a champion for it.
Right. So in at least timeline so far, we have Copernicus, Galileo, Kepler, and Newton in our timeline.
No, Newton's like 1500s. Newton's before Galileo.
I think
is Newton before Galileo?
Yeah.
I know he developed calculus in 1671. I don't know when Galileo died, but I think it was in the 1600s, maybe. I think there was a period where Galileo and Newton existed concurrently, but I think Galileo might have been older.
Yeah, I think you're right. Yeah. Yeah, Newton was later 1600s and Galileo was earlier 1600s.
Okay.
Look at everything I'm learning.
Never too young to learn stuff or old to learn stuff.
Yeah.
But speaking of learning stuff, Leo looks pretty young, and I don't know how young you look because you're just a picture on the thing.
No, I'll take that as a compliment. Thank you.
So, did you grow up before or after? Because I grew up before the big reveal. But you guys, did you grow up after the Pluto got kicked out of the Planet Club?
I grew up with Pluto as a planet.
Yeah, I grew up with both.
Yeah, I was in my 20s when that got kicked out, so I had to learn it in school with the 9 planets.
Yep.
I'm gonna go back and say, "Hey, teacher, you taught me wrong information." I was kidding.
It wasn't wrong information at the time. We didn't have dwarf planet. We didn't care. We didn't care as much about dwarf planets at the time, but now that we have a better definition of them and we can ascertain this information better, you gotta classify it as it's classified.
Yeah.
Mm-hmm.
But we're not the only ones in orbit and stuff. The sun itself is actually orbiting the galaxy.
Mm-hmm.
Mm-hmm.
That's correct.
Yep. It's orbiting the great attractor, right? That's in the center of the Milky Way.
Yeah, the supermassive black hole, Sagittarius A star. Yeah. So orbital period is 200. The orbital period of the sun around the Milky Way galaxy is 225 million years.
That's a long time.
That's a very long time.
So let's see. Last time it was in this position was about the Triassic period.
I don't know enough about the periods of biology and archaeology, not archaeology, paleontology to know what. Right. 225 million years ago is all I know. That's the last time we were here. Okay, yeah.
It's been a bit.
So I know 250 million years ago was the Permian extinction. So yeah, history. Yeah, even though I'm not the expert, I've always loved history.
Hey, good. But yeah, it's kind of crazy to think that, and also that galaxy is moving through the universe, and the universe is expanding into something, like maybe. So like actual concrete Cartesian coordinate the universe, we've never been in the same location. Like we're spinning around a spinning that's spinning some spin. you know.
Mhm.
And I know flat earthers use that as a mocking sentence, but it's not mocking. It's cool and it's awesome, and they should respect it.
Exactly.
So
The sun, I believe, orbits at a speed of about the whole solar system is moving through space at roughly, what is it, about 515 miles per hour, I think, something 515,000 miles per
There you
hour.
go.
Excuse me, somewhere
That's
in there.
when I teach like units and all the zeros and scientific notation. One of the questions I like to give students is to calculate how fast we're moving around the Milky Way, because you can easily figure out the Earth around the sun, but then can you figure out the sun spinning around the galaxy and all these other things? And like 5 minutes ago, how far have we traveled in total space? That's cool stuff to figure out.
Yeah.
So what do you say to the people that say use the argument that we can't feel us moving, we can't feel us rotating, we can't feel us orbiting, we can't feel the whole system moving around?
I would just ask them, have you ever been on a train moving at a steady speed as it crosses a bridge? Because a bridge is very rigid where the ground isn't. There's times where if you close your eyes, you don't know that you're moving. If you've ever been on, there is a ride at the Iowa State Fair. It's called the Ye Old Mill, and it's sort of like a log style ride, but it doesn't go up hills or anything. It just kind of does a weird loop thing. It's got different pictures and stuff that you can see that are illuminated by lights about the history of the state fair and everything. But in between those, it is so pitch black you couldn't see your hand an inch away from your face, and except for when because as it's moving, it's got like, some rubber on the edges and it kind of bumps up against the walls. But in between, when it's bumping up against the walls, outside of that, you can't tell that you're moving. That's how dark it is. You cannot tell that you're moving. So there are instances in physics jargon, if something is moving at a constant speed with no change of vector and even a slight dip in the ground, or all like when you're driving your car, the friction of you going down the road, all the cracks and the dips and everything, those are changes in vector, because those will slightly affect your speed and or the direction in which you're traveling. So if there's absolutely no change of vector, you would not be able to tell that you were moving if you couldn't see things moving around you. But we can tell that the Earth is moving because we can look at the parallax of stars. But we're so small compared to the Earth that we're not capable of experientially detecting its orbit or its spin.
Yeah, 100%. I would add to that, another good example is think about things that very obviously can be seen to be affected, like a cup of coffee, for example. You can be going 100 miles an hour on a train and the coffee is sitting there, it's doing just fine. Put the coffee out the window, it goes flying out, because the coffee can tell that you're not moving relative to the train is moving. So, yeah, and that's exactly kind of what's happening on the Earth. Even though the Earth is spinning, you can't tell because you're spinning along with it. It's the change in change in vector, as Leo was saying.
And another thing is the I believe it's the Foucault's pendulum indicates that the Earth is rotating. Because and people have made there's actually one at the Science Center of Iowa, a 24-hour clock with a pendulum, because if you were looking at it from the bottom looking up, you would see that pendulum make a figure 8. Now obviously it's going to be very hard to visually see, but over time it will make a figure 8, and that figure 8 will kind of sweep and so it will precess as it makes that figure 8, because it's feeling, that pendulum can feel the momentum of Earth's rotation. The only place I think this doesn't happen is the poles. There's a difference in how that pendulum sweeps out, then the angles and everything as you move from the equator to the poles, which again tells us that the Earth is spinning if that changes from equator to pole.
Yeah, because the further you are away from the center, the faster you go. Think about a merry-go-round, right?
Yep.
Well, faster you go in circular momentum, not in like angular momentum.
Yeah.
Nice. So I know this is mentioned a lot for the climate change people, but do you know anything about what's it called, the molecular cycles of the Earth?
Oh God,
and stuff?
I know that word. Oh my gosh. That's one of the problems with talking science online. Everyone's always got that thing that, I remember that 5 years ago, but
There's like 3 different things about how the Earth moves in the orbits and stuff.
Milankovitch cycles.
Yeah.
I think I found it. Milankovitch. Describe the collective effect of changes in the Earth's movements on its climate over thousands of years. Yeah, I know what this is. Leo, you familiar?
I actually am not. This is one thing I don't think I've heard of, and if I have, I never remember the term Milankovitch cycles. Describe the collective effects of changes in the Earth's movements on its climate over thousands of years.
So
I'm assuming. I'm sorry. Go ahead.
So the Earth wobbles, right?
Precesses about its axis. Yep.
Yeah. Well, precess. Yeah.
Yep.
Wobbles is the nicer way of putting it. Everyone knows
precesses like this. If the bottom of the axis were fixed, it sort of sweeps out a precession, but a wobble. Like if you spin a top and they kind of wobble. The technical term is precession, but yeah, most people probably know it as a wobble.
So, and since it wobbles so much, year to year to year to year, you're getting different amounts of solar energy. You're getting different things that can affect the climate to the Earth, and you can track this stuff back through time. Essentially, see. You can try to connect this idea to climate, and back in the day, things were warmer. Well, maybe that's because during that particular part of the cycle, we're getting more energy, or X, Y, Z other thing. I think that's kind of the idea that's going on there.
Mm-hmm. Yeah, that makes a lot of sense too.
Yeah.
I was bringing it up because it's kind of the other part of it, I think is how we orbit the sun too. One of the other two, I think, if I remember correctly.
Yeah, well, all this stuff cycles, right? I mean, in orbit, by definition, we're collapsing in on the sun slowly, right? Back in time, we were further away, and we're getting closer, so we're feeling more energy-ish, quote unquote, kind of. Yeah. But not really anything noticeable. But
God, this
and
is
of course, the sun
new
is moving and all these other things. So
I'm gonna have to use this in future discussions. These Milankovitch cycles.
Nice.
Figure out how to pronounce it. I have no clue how it's pronounced.
Yeah, it still says that it is hypothetical, that there are a lot of observations consistent with the hypothesis, but that it doesn't. There are things that it doesn't explain, so it is still a hypothesis. But it sounds something more like the Theia collision hypothesis for how we got the moon and why the Earth rotates and precesses and is tilted on its axis. But it will probably never move to being a theory because we can't just get in the TARDIS and go back and look at that event happen, but it is consistent with a lot of the observations that we make. So I'll say it's reasonable.
Nice. I'm glad I gave you possible future ideas for future debates and stuff.
Yeah, it just, all these sciences are super, super, super complicated once you dig into them, right? These Wikipedia pages are more math than they are words sometimes.
Exactly.
And that's
very true. I can't tell you how many I've read, and I'm like, there's not even words. The only letters are in the equation.
Yeah, and they're all Greek letters, and superscript at that.
That's why I like people interviewing some people like that, like this, because sometimes they can, sometimes they can admit, oh, I was wrong about that. I can admit that.
Mm-hmm.
Yeah. But yeah, I mean, there's so much variety to the climate and the rotations of the Earth and stuff like that. Like, technically, large volcanic eruptions can have an effect on the motion of the Earth and its wobble. Its precession and all these other things, right? So, when a volcano goes off, it's basically like a gun shooting the Earth at a certain angle, and that throws its wobble off, and that can affect seasons for years to come as it wobbles back on top. So,
can I ask you a question about that? I just want to know if it's true. I've heard this; it seems reasonable, but is it true that either an earthquake or a massive volcanic eruption is why the Sahara Desert became a desert? That it was like a less than 5-degree change in how the Sahara Desert was angled toward the sun, and I think it was either an earthquake or a volcano sort of quote unquote shook the Earth enough to cause it to wobble just slightly, and now the Sahara Desert's a desert, or is that probably not something that's accurate?
I've heard that before. I haven't dug deep into it, but the Saharan desert was once lush.
Yes.
Not now. And the Saharan desert doesn't necessarily line up with every other desert on the planet. Like there's deserts at the bottom of South America, but not in the middle, right? So I've heard that. I think it's more accepted than not, but I can't give you any specifics on it.
You mean it didn't dry up after the flood?
Nope, apparently not.
There is another hypothesis, but I'm not really going to give you a lot of backing for it. So, African humid period.
I looked it up, and it says that it is due to the precession of the Earth, but that it wasn't anything caused by some specific geologic event. It's just the typical precession of the Earth over the years. That angle slightly changed. Now it gets a little bit more sunlight. Whoop, zoop, sloop. You've got a desert.
Yeah. And once the desert starts, it keeps growing and expanding out.
Mm-hmm.
I have heard the geology component of that too, but I'm trying to find where. So
I don't know if it was proposed as a hypothesis that, well, maybe, because I don't think it was very long ago that it was pretty lush. And some have proposed, I think, that, well, the Earth couldn't have precessed enough to change the angle meaningfully to cause a desert. So maybe something else caused a little bit more wobbling to occur.
Yeah, there's tons of geologic events, on a global scale. I think there was a volcano some 100,000 years ago that people associate with the bottlenecking of genetic information in humans, for example.
Well, actually,
when we dropped down to like a really small amount of people in Africa, that timed out with a volcano that was essentially the largest we've recorded while humans have been around.
Apparently, that might have been, according to my friend Erica Gets It Given, that might have had nothing to do with each other.
They might not, but it's a conversation people have.
Sure.
You know?
Yeah.
And so, as geologists, we want to make sure volcanoes are involved in everything. So, that kind of brings in the bacon for us. So,
yeah, I bet.
Yeah. Oh, she's my primate expert. And
Erica is, oh God, she is phenomenal, and she is so goddamn smart. Sorry for saying that, by the way, but God, she is intelligent.
Don't worry, I'm not monetized anyways. So.
Okay.
Yeah, definitely take her word on evolution over mine. But I'm just spitting out stuff I remember hearing back.
Yeah, that's what that's what I heard too back in the day until. Me, her, and Jackson Wheat had an episode about bottlenecks last year.
Nice. Oh gosh, what am I looking up?
What can we talk about? You said, how did what did Einstein theories affect our knowledge of the planet's orbits, or did they affect it at all?
General relativity did. One of the things that it was capable of explaining was also this happening was predicted by the model, and so if the model gave an explanation for it, was something that Kepler's laws could not account for, and neither could Newton's laws, was the precession of Mercury's orbit. So it's hard to describe a precession for just a planet that's spinning but not orbiting anything else is simple. If you have its axis, if you were to say fix the bottom of it and have the top of it sweep out, sort of like a cone, you would call that a precession. For an orbit, it's a lot harder. Imagine the elliptical ring, and as that planet comes in, that it will sort of over time as it orbits, it would make like a flower pattern, so to speak, because it speeds up as it gets closer to the sun, slows down as it gets further away, speeds up, slows down, speeds up, slows down. And so you would eventually get a flower-like pattern of all those elliptical rings that represent the orbit all the way around. It would look like a flower pattern, and that's orbital precession.
So it's not like one straight orbit every time it's moving.
Mm-hmm. I could draw a picture of it, but it would take about 3 minutes to get my iPad queued up and everything, so I'm not going to do that. I don't have the ability. But I could be able to draw it and it would look intuitive. But yeah, it's essentially, it doesn't make the same exact path. That orbit might be here, but then the next time it's like here, and then 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 here. So like I said, if you took it all and added it up, it would look almost like a flower pattern. And they call that orbital precession. And general relativity predicted that. Do
we know how long that takes, or any idea?
I No,
For,
I do
for,
not know.
for a full flower for the full
For the
flower
full
that,
pattern of form, yeah, I don't. I'm sure somebody's probably worked it out somewhere, but I don't know. I could try to look it up.
I was looking at that. I was looking that up. I heard this is more get flat earthers and stuff than geos. Probably have to do geocentrics too, but that the orbit of the stars look differently. Different. We have different stars or constellations on the southern hemisphere, and we had the northern hemisphere.
Yep. Yeah, very much. The constellation everyone's familiar with is more or less, to my knowledge, from like the Greek constellation, which is northern hemisphere, right? So Sagittarius and Pisces and all those other things, they don't all exist in the southern hemisphere, and the religions back then had different gods for their stars for a reason. There's not a one-to-one line up because your view angle of the sky is different. You're looking up versus you're looking down, since it's a globe. And then those those constellations themselves have changed place over time as we travel through the universe. So stars that were in certain constellations at the time of the Greeks now are in different constellations. So
Yeah, I also heard that some the dates of the constellation might shift too. Since we're moving the orbit is 100% 1 year 1 day that the constellations periods might be shifting from each other to like a Gemini might have been in like March whatever in the past maybe let's go back far enough.
Yeah, that's horoscopes are crap for 1,000 reasons, but on top of all those, they're inaccurate even to themselves now. They don't, because they don't change, they don't track with this stuff.
Yep.
So since the stars aren't circling the Earth once a year and stuff, how does the Earth like? So they're like around, let's say around the sun. I'm saying, but like, how do we observe these constellations if we're going around the sun? Each year?
They're just so far away that their position change relative to us can be measured with telescopes, and we can measure the parallax. But for us, I mean, a lot of the reason why we don't experience like the massive change in the position of stars or feel things like Earth's rotation is because humans are very, very small in the universe. And we also exist for very short amounts of time. Most things that happen, especially on cosmological scales, at minimum are going to take thousands of years for there to be any measurable or noticeable difference. So with humans, there's a lot we just won't ever really experience because we're just not privy to the time periods that would allow us to have the experiences of those phenomena.
Yeah, I always wondered. I wondered or not if how many stars if we got to see the stars anymore. Sometimes the stars where I live, the stars aren't that visible anymore. But how many of the stars up there we're seeing are already dead?
Most of them actually are probably still there.
It's tough to tell, though. I mean,
yeah, because the stars that we can look at least that within a reasonable, I mean, depending, you could see any star in the Milky Way galaxy depending on how powerful your telescope is. But I think it's something, isn't it like something like Orgaz, and it's like 5,000 or 6,000 stars are actually all that's visible like, with the naked eye in the night sky or something like that.
Yeah, because the brightness of the stars doesn't overcome the sun.
Yeah,
so the sun has that glare that goes out, and we're like sitting in the glare. So even at nighttime, the glare is coming at you from the other side.
Yeah.
Right? If I take a flashlight, a really strong flashlight, shine at your back, you're not going to see as well.
Exactly. But yeah, most of the stars that we can see and that we can study that are close to us, like Betelgeuse is a good example. We're expecting that within the next 100,000 years, it will likely go supernova, but it's 643 light years away from us. So anytime we see a change with our telescopes and what's going on with Betelgeuse utilizing visible light, that change actually occurred 643 years ago. It just took the light that long to get here. But it doesn't appear outside of Betelgeuse because I mean, in the history of the universe, 100,000 years is pretty quick. And for our periods it's not. But I think other than Betelgeuse, I don't think there's any other stars that are expected to go supernova anytime soon.
I was just curious about that. Like, since it takes so long for light to get to us, and is that star dead already?
All these conversations, to a certain extent, are calculation more so than observation, right? Like, we have an idea of how old Betelgeuse is, not because we watched it be born, but because we look at the amount of radiation it's giving off, and we throw that back into our charts and our calculations. We're not wrong necessarily, but we may be off by 10,000 years in Betelgeuse's age. How do we know?
Yeah,
you know?
Yeah. And with a star like Betelgeuse, being off by 10,000 years isn't going to be meaningful. So, I mean, when we say, a star is...
Yeah, we got talking
80 million, 80 million years old, give or take, 33,000 years. 33 might sound like a lot, but when you consider the star is, roughly 80 million years old, that's like saying, oh yeah, he's 23, give or take 7 weeks.
Exactly. It's super cool stuff, super fascinating stuff. And of course, to add on to that, we can study stars more than just visible light. Right,
yeah,
the
exactly.
entire EM spectrum allows us to study these things.
Yep.
Gravity, and all these we can study the gravity of the planets and all that.
Yep.
And it's all stupidly cool.
Yep. And spectral analysis is a really, really big one, especially for studying the composition of the stars, because obviously certain atoms have a certain give off particular spectral lines due to the emission absorption lines. So, and the structure of a star can also tell us a lot about its age and things like that, because it can tell us what generation it is. The more, and I'm going to use metals for astronomy, which is just anything heavier than hydrogen and helium. We can look at what's called the metallicity of a star, and that will tell us how young or old that star is.
It's probably not true or not, but when I first heard about black holes and the galaxy, I always wondered maybe if they were the very first stars the universe made, and then all the stuff the galaxy were born from those stars. They became black holes.
I want to say the cycles happened 2 or 3 times already.
Okay.
Like the black holes that we have now would be like the exploded stars already black holes, already exploded, already black holed. Because star lives are in hundreds of millions of years or whatever, but the universe is billions of years old.
Yeah.
So like I think we're pretty young in terms of stellar life. Like the atoms that make up you have gone through a lot of crap in their time.
Yeah, exactly. In terms of how black holes form, really it depends. I mean, if we're talking supermassive black holes, which are at least thus far exclusively what we found at the center of galaxies, we're not quite sure how they form. Okay. It's been proposed that supermassive stars, whether they're baryonic stars or a hypothetical dark star, which is a star that is driven by dark matter decay reactions at its core rather than thermonuclear fusion, these would have been astronomical units in diameter, where stars are now, or maybe hundreds of thousands of miles in diameter. It's possible that those could have collapsed into black holes, but the main problem with stars being the source of supermassive black holes is that, given how old the universe is now, it's our models and our simulations are not capable of giving a large enough mass based off of just accretion or even black hole mergers. The black hole mergers do not happen very often, especially with supermassive black holes that aren't supermassive. So, in short, there's probably some sort of primordial structure in the universe that preceded or was around the time that the first stars formed that gave rise to the development of supermassive black holes. But there's hypotheses out there, but most cosmologists are going to say that we don't really know how supermassive black holes form, which I suppose if it's your thing, I guess means God did it. Because where science doesn't have an answer, it must necessarily be God.
Yeah. I mean, black holes is such a ridiculously cool topic. I mean, did you know there's micro black holes?
Mm-hmm. Yeah,
There's
we've
black
made them.
holes. Yeah, exactly. Right. There's little dots out in space that are technically black holes that we can see like warping space and stuff like that. I mean, like I'm talking like the size of a desk.
Yeah.
You know, and
Because
that's
black
just
hole,
crazy to think about. Like
Speaking of black-
you'd be driving along in space and suddenly, whoop, black hole.
You're gone.
speaking of black holes, I know this is more sci-fi and science fact and stuff, like on shows, but is there I've heard on Star Trek or something, but that some black holes are wormholes and stuff.
There's ideas of that. Most of our physical models don't really grant that.
Yeah.
The biggest reason for the black holes being a wormhole or like leading to a white hole is the fact that essentially the curvature in space-time goes to infinity, because it's so this is one of the reasons why I'm big on, if I need to, correcting or at least explaining what a singularity actually is, because I find that a lot of people think a singularity is some sort of physical object, that it's something that's extant in reality, and they're not. Infinities don't exist, at least quantitatively, in reality. A singularity is, in technical terms, what happens when some function becomes non-differentiable along some asymptote, or that the limit of that function is undefined. So it's like for the function f of x equals 1 over x, with the limit being x tends towards 0, is undefined, because you can't 1 over x, if x is 0, you can't divide by 0. That would be an undefined function. It would be a singularity. If you have a function that asymptotes the y-axis, where it keeps going up and up and up, but you can keep zooming in, but it never touches the y-axis, it just infinitely approaches it. A function along that asymptote will be non-differentiable, i.e. you can't take the derivative of that function along that asymptote. It would be considered a singularity. And that's what happens with the functions that we utilize in general relativity. So we say that at the center of a black hole, you get a singularity. The mass is not literally infinite. What's really happening is space-time and the structure of space-time changes so drastically that general relativity as a classical physical theory is just no longer capable of describing it.
All right. Some movie a few years ago. Did you ever see that movie? I think it was called Interstellar.
Interstellar?
Yes, very good movie.
Great movie.
Yeah, I ever once seen the movie. They were trying to find planets near a black hole, and they were on the planet for like 10 minutes or 30 minutes, and like 30 years up or something passed up on the ship above them. Mm-hmm. Is that accurate?
Yes, time dilation. So time dilation it's an effect in special relativity. The first, we've seen it, we've measured it, we actively have to account and correct for it with our global positioning system. So first off, in special relativity, the manifolds that you're utilizing are not like a typical Galilean or Cartesian coordinate system. You can take the axes and you can move them. You can do this. You can't like cause curves, that would be general relativity, but you can keep them not parallel, but what's the word? I can't think of the word. But the lines will always stay straight, but you can change their angles. And when you do that, you can change the amount of time that elapses on a clock. So in general relativity, if you get close to a black hole, space-time curves. So your clock will read more elapsed time than somebody who's, say, very far away from the black hole observing you fall into it. So your clock will be ticking much slower than theirs, and we call that time dilation. It's colloquially, you'll often hear time slows down. That's not, in the colloquial sense, that's not inaccurate, but in a technical sense it is, because time isn't doing anything from which it could slow down to begin with, because time doesn't move. We move in time. Time doesn't move around us. So technically speaking, you would say that two different clocks can read two different times, or time can pass on two different clocks at two different rates. But to say that it slows down, again, technically speaking, is incorrect, although saying time slows down is not really inaccurate when you're speaking, to a lay audience.
Yeah, I brought that up because it reminded me of the movie reminded me of something when so I think some YC creationists bring that up that the Earth is in the middle of one of those things, and that's why the Earth everything seems older out there.
A time sinkhole. Mm-hmm.
You've heard that argument before?
Yep, I've heard this argument a lot. Oh, well, the Earth is 6,000 years old compared to the rest of the universe. It's so young because, space-time curves, and so the Earth is curving space-time. So time is different for us, which is true, but not like that. No, the Earth does not have a strong enough gravitational field to make it 6,000 years old relative to the rest of the universe.
I was thinking, if that was true, wouldn't that mean all the astronauts that went up in space be a lot older when they got back?
Yeah, they would probably be. I mean, they'd get back, and everybody else would be dead if that was the time difference between being on the Earth and being not on the Earth.
Yeah, those ad hoc arguments never really seem to hold up too well.
Exactly. Almost like they pulled it out of their ass at the last minute to justify a belief that's already falling apart.
Almost.
Yeah. So what else we got to talk about?
Orbits. Orbits and stuff. Why? Like, I don't know if I've heard this before, but why did the why is it past the asteroid belt until we get to the Kepler and Oort cloud that those planets are more gassy but we're more rocky?
Oh, there's a term for that. Shit. Shucks.
Yeah, there is. But the simplistic explanation for why is that heavier material will fall inward more quickly, or will work its way inward more easily than lighter mass material, and so everything on the outside will generally turn. It is going to be a gas. It's also, you're further away from the sun, so there's temperature variances, and that can have a play. So further out, you're likely to get massive gas giants, and closer to a planet, you're likely to get terrestrial, or closer to a star rather, you're likely to get terrestrial planets.
So was there any chance, I don't know how big a dwarf star is that Jupiter, other guys can be a dwarf star or star themselves, or is that not possible?
Well, Jupiter could become a star, but it would need about 70 to 80 times more mass than what it currently has.
Okay.
Yeah, Jupiter's big, but compared to a star, Jupiter's tiny.
Okay.
Exactly.
Oh,
yeah.
I cannot remember this.
I don't know how big, because I heard Jupiter was one of the reasons that the asteroid belt was its own planet or something.
I think it's the inner asteroid belt. I think it's because it goes the asteroid belt, the Kuiper belt, and then the Oort cloud. And I think it's the innermost one, I think, which is just called the asteroid belt.
Between Mars and Jupiter.
Yeah. So the thing is, where Jupiter is today is not where Jupiter formed, according to all of the simulations that we have run. Neither are Mercury, Venus, Earth, and Mars original to the solar system. We live on a second generation planet. We've never observed this, but all the simulations that we've run, in order to get our solar system to look the way that it does, this event had to happen. Jupiter would have formed out much further out in the solar system than where it is now. In the inner solar system, there were 6 super Earths instead of the 4 tiny little rocky planets that we have. The thing is that Jupiter was orbiting rather slowly. It's massive, and it's further out of the solar system, and it started to migrate inward. And as it did this, its gravity sort of had a wave, I guess you could say, of a bunch of rocky material and everything that it was pushing. It's flinging all of that into the inner solar system, and its own gravity is affecting the inner solar system as it migrates closer and closer to it.
Okay.
And that did one thing. It destroyed any hope of being existing long term for those 6 inner terrestrial planets. Their orbits were disturbed. They broke apart. About 90% of that material fell into the sun, and the 4 planets, one of which we live on, that are in the inner solar system now, Mercury, Venus, Earth, and Mars, formed from the remaining 10% of that material. The reason that Jupiter is not all the way in the like sitting where Mercury is, which is otherwise where it would be, and it would be what's called a hot Jupiter, which is gaseous planets like Jupiter, Uranus, or Saturn that end up very close to their stars, and their atmospheres begin to boil away. Those are called hot Jupiters. The reason that did not happen to Jupiter is because there was another guy hot on Jupiter's ass that pulled him back. Not really pulled it out, but kind of yanked it out a little bit and stabilized Jupiter's orbit, and that was Saturn.
So was the called the Theia planet? Was that the Theia planet? Was that one of the super Earths, or that?
No, that was a Mars, roughly Mars-sized object that probably formed along with the 4 inner terrestrial planets.
But it just happened to be on our orbital path.
Yep. And the object is still in the sky today. A lot of people think it makes you go crazy when it's full.
So, how have satellites affected our knowledge of our orbits and solar system stuff?
Pretty well,
they allow this conversation to happen, for one.
Exactly. Yeah, they've allowed us to. I think we've measured a lot of the orbits of other planets utilizing our satellites.
Yeah. So satellites as telescopes is super, super, super important because we have an atmosphere on the planet. And if you can stick a telescope of any part of the EM spectrum outside of our atmosphere, you don't have to worry about accounting for the energy coming through the gases like that. So that's why the Hubble was so important, because you could take pictures that you physically could not take on the planet. And just the amount of information you're able to gather in that manner is stupid.
And our satellites have evolved, I guess, since our Voyager days to now. They're better than they were. Oh
yes, very much so.
Well, I would say the satellites themselves I don't think have changed much, because throwing something through the sky isn't super changed, but the machines on the satellites.
Yeah, a lot of the technology on them. Yep.
Yeah, the computers and stuff.
Because I heard the Voyage, at least the Voyager ones are probably going to be dead. If they're not dead already, they're going to be dead soon.
Well, Voyager 2, I think, is still transmitting data.
Yeah, I think both of them are. I think both of them are.
Both of them are?
Yep, and both of them are outside of the solar system.
Oh, I mean, they've already passed the Oort cloud.
They've passed beyond the Oort cloud. They are officially past the heliopause.
Oh, I didn't. I don't know that far yet.
Well, what was the one that we just sent past Pluto? What was that called?
Oh,
Well, I'm bringing it up because Voyager 2 was famous because they pointed it back towards Earth and took a picture of
pale blue dot
where Earth would be, right?
Mm-hmm.
And the one that just passed Pluto like 4 years ago, they actually pointed it towards Voyager 2. And they took a picture of where Voyager 2 would be at that exact moment. And that's just crazy awesome. Because it's basically, they point out into this random chunk of sky, but they could calculate where Voyager 2 would be. You can't see it, obviously, but just that idea of being able to rotate and know that stuff is so cool.
Mm-hmm.
I was wondering, because I know they do video still, but can we send a, if we did it nowadays, can we technology wise, can we send a satellite to where all that
New Horizons is the one I was talking.
There you go.
Oh, and do videos now? Like, I probably couldn't do it back then in the 70s and they launched Voyager, but is it possible to do one now? Video camera last that long?
It's possible. the biggest aspect is going to be finding a way to protect the camera in such a way that we can still actually see things with the camera. But in a lot of ways, it would be completely useless to have I think both the Voyagers did have a camera on them, but for like continuous video feed or continuous video recording, would be essentially pointless because 99.99999999999% of anything that it ever records, even if it existed theoretically forever, is going to be nothing but blackness.
True.
Because I mean, it's the universe. The universe looks beautiful in all those pictures, but if you could be shot through the universe, and this is going to be a little bit contrived, and I'm going to ignore some technicalities, but if you could be shot just into the universe at the speed of light, you didn't have to worry about eating and the pain of being in the vacuum of space and the radiation and all that, and you didn't have to deal with time.
You were
essentially being stopped. Yeah, you would see pretty much nothing for 99.99% of your journey. Would be just nothingness.
That's true. I was just wondering if our technology was that advanced yet.
We could probably do it, but yeah.
If you're familiar with CGP Grey, he did a video not too long ago, basically taking a piece of paper and then folding it in half down so small down to the plank, and then doubling it so big out to the universe. And he talks about in that video exactly what Leo said. The amount of emptiness in the universe is like Lovecraftian in concept. Like it's you can't grasp that much nothing. You know.
So this is not a thing. Is it just the money or lack of interest that after the 70s we stopped going as far as the moon, and the space stations, and we never went back to the moon after the 70s, the Apollo programs? Do we just lose interest, or we lose money, or what?
I think who you ask will give you a different answer. That being said, you could definitely blame Nixon for that, because Nixon decided to switch from exploration to near Earth orbit stuff. Switching over to, the Russians have Mir, we need something, and stuff like that. Well, they have Mir at the time, but Russians had a space station like in the early 70s. So we need to beat the Russians, and Nixon purposely changed that.
Yeah, I did also want to correct myself quickly. The Voyager 1 and Voyager 2 now have passed the heliopause, but they have not passed the Oort cloud. The Oort cloud extends very, very far out. I don't even think they've touched the Oort cloud yet.
So what's the difference?
The Oort cloud, so the heliopause is essentially the place. This is hard to describe.
Have fun.
It's really, really simply, and this is almost overly simplistic. It's where the majority effects of the sun's magnetic field sort of come to an end and yield to interstellar space. And again, that's almost overly simplistic, but it does kind of draw in your mind an idea of what the heliopause is. So if that's right here, and then you've got, say, the sun right here, it's going to look like the comet. You're going to have the heliopause, and it's going to come out to a long tail. The Oort cloud is going to extend. The Oort cloud extends, I think, like 3/4 of the way to Alpha Centauri, which is 25 trillion miles away from us. So the Oort cloud extends very, very, very far outside of the heliopause. I think that they do consider the Oort cloud as part of the solar system. And this is the thing with things in space. Like same thing with our atmosphere. It's really hard to draw a defined line and say that's the end of the solar system. Just like it's really hard to draw a line and say that's the end of our atmosphere. It's kind of just a gradient.
Okay. So the heliopause is like where the sun's light or energy stop being even effective, give or take.
In some senses, yes.
But then the Oort cloud, which might be part of our solar system, might not be. It goes even further beyond that.
Yep. It goes much, much further beyond that. I think the heliopause is, because it's logarithmic, is 100 times further away from the sun than it is from. It's 100 times further, 100 times Earth's distance. I'm trying to think. I know it's logarithmic, and then the Oort cloud is like 10. I think from like 10,000 to 100,000 times that distance.
It's a big long distance.
Yeah. It's logarithms were never my strength.
Yeah, so we know how the asteroid belt might have formed. Or we have a hypothesis about our theory, but what about the rocky bodies like in the Oort cloud and Kuiper belt? How did they get way out there?
I think a lot of that is just material from when the sun would have been forming
Okay.
that really just never coalesced into a planet, and kind of everything spread out, and it just kind of formed sort of a quote unquote cloud that surrounds our solar system.
Man, you need a cough drop or something.
You good?
I think so.
Ooh, buddy.
I hate coughing. That's the one thing I can tell you, especially hard coughs like that.
Yeah, I have asthma too. So
Okay.
and plus,
I would get you a glass of water, but I don't think you would get
actually,
it. So.
I have one.
Okay.
Oh, nice. He's ahead of the game.
Yeah.
Yeah. I also got my I'm since my in the Twitter feed. I also got my second COVID shot Friday.
I saw that. Yeah.
I'm still feeling better now, but I'm still feeling the after effects of my immune system going to work on the thing.
Mm-hmm. Which one did you get?
I got the Pfizer one.
Okay.
Yeah, I was lucky. I got the Moderna shot. I got both of mine, and I had no effects, like absolutely nothing. So I was lucky.
I guess I'm the lucky. I'm the unlucky. How many percentage in the clinical trial had side effects? But yeah, well, that's better. I say it's still better than the actual disease, in my opinion.
Exactly.
Very, very true. Very much
Leo, according to NASA, they're putting the Oort cloud starting at 2,000 to 5,000 AU and ending anywhere from 10 to 100,000 AU.
Okay.
So
Alrighty.
it's stupid big, yeah.
Yeah, it's ridiculously thick.
Yeah.
And the thing is, you could go through it and maybe not ever visibly see another object.
Exactly.
Like it's insane.
And that's even nowhere near the next star.
Yeah, I mean, shit, 25 trillion miles from the sun to Alpha Centauri. Oh, God, that is an insane distance. And that's right next door, galactically speaking.
Yep. We just need to sail there, I'm telling you. Everyone YouTube hates it, but we need to sail there. That's my answer.
And see, that's the thing. Solar sails would be very good for doing interstellar travel. I think that some say that it's the intergalactic travel where you would only be able to get to a certain speed past which it's not that they couldn't work, but they might not get you to go as fast as some other types of technology would. I'm curious though as to how far humans will take the ability, or rather how far humans will get in the technology that they develop for space travel. Will we ever actually get to a point where we could, even if we don't use the technology for this, theoretically travel to another solar system feasibly?
Yeah,
and I think a lot of that has to depend on how well we take care of ourselves and the planet that we're currently on.
Oh, you had to ruin it, didn't you? You had to bring that into it.
So
what can I say?
It's like if we could travel at the speed of light, it would take us at least 4 years in the Alpha Centauri or something like that. Or,
yep, 4.2 years.
Yeah, I guess that's why in the Star Trek and stuff in Star Wars you're even faster than light speed because you have to be.
Yep. Which superluminal speed is we know is not according to our current physical models. Some physicists might take it a step further than me, but me being a non-professional, I'm going to say according to our current physical models, superluminal speed is impossible.
That's used in sci-fi, the superluminal speed.
Mm-hmm. Chances are it's probably not something that could actually ever happen in reality, but science is tentative. You never know. We do find tachyonic particles, but chances of that are I don't get your hopes up. That's what I can say. Do not at all get your hopes up for superluminal travel.
It's true because according to there we only have 40 years till it's invented.
Mm-hmm.
Low, but yeah. Oh, so
what's next on the itinerary?
I'm probably gonna bounce out here in 10 minutes or so. By the way, I gotta go to bed.
Yeah, I think we pretty much did everything. We talked about orbits. I think we talked about everything. Basics at least. We talked about why people used to think that everything was around the sun. We realized wrong. We got the timeline almost. We did. I think it was like Copernicus. I still the timeline still iffies me. From what it's Copernicus, Galileo, Kepler, Newton, Einstein. Probably some people after him, before him too. In between.
Yep.
Yeah, there's
Just
1,000 scientists in that conversation.
yeah, on that point, really quickly, because these people helped. They sort of paved the road that Einstein then came down, and then Einstein took that road a little further. People like Michael Faraday,
Yep.
Gauss. Is it Friedrich Gauss? I believe is his first name.
I'll
I think
accept
Friedrich. And James Clerk Maxwell and Oliver Heaviside, who and for me, most people know the equations as Maxwell's equations. I don't call them that. I call them the Maxwell-Heaviside equations, because Oliver Heaviside made significant contributions to classical electromagnetism, and almost nobody knows his name.
Oh,
So when I found out about his name, I'm like, we got to do this guy some justice. They're the Maxwell-Heaviside equations, and those equations do not work under a classical field theory. We do have, well, I shouldn't say that because special relativity plays into that. It's in a in the framework of classical mechanics. That's what I meant to say. Electromagnetism.
You say classical? Do you mean like the Greek classical?
Classical, in terms of physics, essentially means not quantum.
Okay.
Because there are
think
differences.
Newton. Think
Yeah.
high school physics.
Okay.
Yeah.
Not like in the BC star era thing. Okay.
Yeah.
They didn't have physics back then.
Yeah, in classical physics, electromagnetism didn't fully work. Some of the symmetries underlying electromagnetism as a fundamental force couldn't really be explained. Certain effects couldn't really be explained. And what we found out is the reason for that is because the kind of manifold that we're trying to define these effects on isn't the right one to use. And when Einstein developed special relativity, that fixed all of those problems. So electromagnetism was one of a major stepping stone on the road to the development. Without electromagnetism, Einstein probably would have never had the thought experiments that gave rise to his development of special relativity.
Cool. And do we have anybody past Einstein that's built on his theories that we have to do now in the last 100 years or so?
On relativity, no. We've utilized special relativity with quantum mechanics, and we get relativistic quantum mechanics, and then more advanced, we get quantum field theory, which is taking a classical field or a classical field theory and applying quantum mechanical concepts like uncertainty and superposition, what have you, to it, and then utilizing that structure to define things. But both general and special relativity have themselves not been modified in any meaningful manner. We might have added some really not entirely meaningless, but somewhat not superfluous. What's the term I'm looking for? Marginal, I guess you could say. Just some marginal terms might have been added to, clean up the math a little bit, but no major evolutions of relativity. But we know with general relativity that there is one, because we cannot give a quantum mechanical description of general relativity. General relativity does not like quantum mechanics.
Is that like the cellular level or something like that?
Quantum level is, and again, this goes back to that there aren't defined lines in reality. It's always a gradient. We've described even very large macromolecules using the principles of quantum mechanics. But when you think of quantum mechanics, generally I tell people think of atoms and smaller.
Okay. So that so far, at least for now, the timeline of orbits and stuff into Einstein for now. Nothing has come.
Yep. Quantum mechanics wouldn't be useful for defining orbits, because it would. The difference between classical mechanics and quantum mechanics is that quantum mechanics is a more accurate and underlying description of reality, but once you start talking about big objects like humans or the Earth or planets and their orbits, you could utilize quantum mechanics, but your equations would be so complex that the world's most advanced supercomputers could not solve them. So what classical physics is sort of an approximation of quantum mechanics to larger scale objects. It's taking quantum mechanics and saying, all this stuff, let's ignore that and approximate solutions, and it works just fine. We use classical mechanics to send stuff into space. We use it to make predictions every day. It works just fine.
Awesome, cool. Maybe go into more details about stuff later. So, you guys have anything coming up in your channel you want to advertise to the viewing audience?
I on my channel I did not do one last Thursday because I had some things going on, but every Thursday at 7:00 p.m. Central Standard Time, I do a Dr. Eigenstate Explains video. It's the flagship series of my channel where I at least try my best, do my best to break down complex topics generally, like I said when we started, in astrophysics, cosmology, and quantum mechanics, areas of theoretical physics, and try to convey them in a manner that's more palatable to a layperson, but yet still retains some technicalities that other communicators might try to gloss over. So I'm trying to find or be more of a middle ground between explaining this to the laity, yet still retaining some technical aspects of the subject so that people walk away as informed about the subject as possible and arguing from what the subject says rather than having to rely strictly on, say, the analogies that a lot of the professionals give to sort of bring the advanced concepts down to a place where the average person can understand it.
Yeah, it's always fun to find that balance between keeping it simple but also keeping it knowledgeable, I guess.
Yep.
Yeah.
Like,
I'm hoping to start a book review series on a mud flood book I found.
Sounds good.
It is the worst. Like if I crapped on a piece of paper, I would have written a better books than this. So hopefully I'll do that soon, and then just my general making fun of people and all that terrible science I pretend I like.
Yeah, yeah. I tried doing that one time. I couldn't do it. Like reviewing a creationist, whatever, or a channel. I just got my brain just died. And halfway through, I'm like, I'll leave to the experts, I guess.
Some of the material can be tough to get through. It's not that it's difficult to understand. It's just difficult to comprehend why somebody would think this would work to begin.
Exactly. It's difficult to keep your head from bouncing off the desk when you're listening to it. Yeah.
Yes.
So I guess I need that. What you guys do, like the breaks of unintelligibility for real things.
Yeah.
But as for me, the only thing coming up to my channel is if I ever get my butt up and stop being lazy is when I start getting back to editing is my next Kingdom Hearts video I recorded 2 weeks ago at this point.
Oh, fun.
But anyways, you guys have any catchphrases you say at the end of your shows?
I say per causam nas perfectum, which is Latin for through reason we progress.
Nice.
I'm not inventive enough to have catchphrases, sorry.
All right. And as I say, never stop learning and enjoy the randomness. We'll see y'all next time.
Take care.